Good morning.
Good morning.
Good morning. This morning good morning everybody in the news, everybody this morning, good morning. Anyone remember that from Good Morning America? Or anyway. Okay, so that was awkward. Who has seen the ribosome video? It's about 10 years old. Okay. Well, my computer fell asleep. But what I'm about to show you is the example of a ribosome in the biological milieu grabbing the tRNAs that have a little amino acid at the bottom and an mRNA strand that goes through the ribosome like a piece of magnetic tape that has some digital information on it and grabs the right tRNA from the cell from the milieu within the cell, and it builds up the protein, and the protein comes out of the ribosome. And what this does is actually prove to you that the concept of a nano assembler, like a nano machine, is actually possible under certain circumstances. So let me go ahead and show this to you, and it's just about just a couple minutes long, and if you've seen it already, it's worth seeing it again. And this is Ada Yonath's group, who's a Nobel Prize winner for discovering the structure and function of the ribosome, along with her colleagues. So don't worry about all the details here, but this is the mRNA. It's the messenger RNA. It takes 3. You learned this in Build 1 probably. Everyone's taken Build 1. Every 3 nucleotide bases encodes a different protein. And he looks a little bit like Grimace from McDonald's with the little arms. And each one of these tRNAs has an amino acid at the bottom, which is coupled by a condensation polymerization reaction to the growing chain end. And this is a polypeptide that's coming out the bottom. Then, when the process stops, the large and small subunit of the ribosome dissociates. And that's the end of the video. Yes, sir? I don't know. Sorry. The question is, how fast is that happening? Much, much faster than the video. So this is, today's lecture will be a primer on biological structures, and what I would like to get to, and today is the last bit of material, new material that will be on the exam next Friday. So we don't have class on Monday because of President's Day. And then Wednesday we will, I haven't quite decided what we'll cover on Wednesday. Yes?
Is this midterm, is it a cumulative or just like what we learned from the last midterm?
It is cumulative. Yeah.
Office hours is Tuesday at noon.
Cody and Mickey's office hours will be Tuesday at noon because of the holiday on Monday. Okay, so today is the last day of new material, and if you're going to be on your phone, you don't have to be in here, right? Okay. So why did I show that video to you? Well, it shows us that if you have molecular control over a nanostructure, a ribosome is a nanostructure. It's like the ultimate in sophistication of a nano machine because it's largely responsible for building us, at least in terms of the protein component. Then it tells us in principle we can do pretty much anything with nanoengineering. So here's the link. It'll be in the notes, but you can get the video there. And when we see images of cells, schematic diagrams of cells, they're often drawn in this necessarily simplified manner, where you have all the different cell organelles and the phospholipid bilayer, which is a bilayer vesicle that we talked about earlier that encapsulates the cells. But what we find, though, is if we look in much more fine-grained detail at this, that it's really a structure that looks much more like this, where it's just almost a solid bag of stuff, where we have different proteins and nucleic acids and biomolecules that they don't coalesce, even though there are very strong van der Waals forces, in part because of electric double layer forces and other repulsive interactions like entropic repulsion due to steric mediated forces that we talked about earlier in the class. So we wouldn't expect, this is really quite a fluid environment, despite the large fraction of solid material. And a protein is made of one of the most useful types of biomolecular building blocks, and that is the amino acids. I know that many of you have seen this before, but here it is again. I remember one time I was at a party senior year of undergrad, and I was a chemist in a room because I have an undergrad degree in chemistry. Sorry. And I was in a room with a bunch of electrical engineers, and the electrical engineer said, "Chemistry, huh? What's your favorite amino acid?" And I forgot what I said at the time, but let's just say tryptophan, because it's in Turkey and it makes us sleepy. Which isn't really the reason you get sleepy for Thanksgiving. It's called food coma. You ate too much. But anyway, the amino acids can be broken down into these 5 groups: the nonpolar amino acids, the aromatic amino acids, not because they smell good, but because they have these aromatic rings, positively charged N groups, the negatively charged N groups, and the polar uncharged N groups. And what's in common with all the amino acids is an amine and an acid group. Okay, so all of these things polymerize. They're like basically like Legos, where the amine group combines with a carboxylic acid group to form an amide or peptide bond in the language of biochemistry. How do these structures form something useful? So an amino acid is sort of like a biopolymer. It's not quite a polymer because it doesn't necessarily have to have the same repeat unit. It doesn't have to have all glycine or valine or isoleucine or tryptophan all in a row, although it could, and then it would be a polymer. But it is nevertheless a macromolecule, so a very large molecule. And polypeptides self-assemble. This is an example of what we would call in the nanoengineering business bottom-up fabrication. This is a bottom-up process where the amino acid residues, this is called the primary structure, of proline, alanine, asparagine, lysine, threonine, and so forth, assemble into a secondary structure. And there are two famous types of secondary structures that we'll talk about in a second. Those are alpha helices and beta sheets. So an alpha helix is where the specific sequence of the amino acids cause it to roll up into a helix. And a beta sheet is where they lie side by side and form a sheet and are stabilized by hydrogen bonding. So this is the secondary structure. The tertiary structure is a single polypeptide chain that largely due to hydrophobic interactions balls itself up, and it has its beta sheets and alpha helices and random coil regions that define the tertiary structure. The quaternary structure is a bunch of tertiary structures stuck together. And these have dimensions of, let's say, tens of nanometers to many microns, depending on how large the protein is. Let's look in a little more detail at the alpha helix structure. There are about 5.4 angstroms, or 3.6 residues per turn. And don't worry about memorizing the structure. You'll have to do that in Nano 103, so don't do it now. But I just want to give you the idea of what the sort of the ultimate in bottom-up nanoscale self-assembly is. The alpha helix, so this is the two carbon atoms. Two carbon atoms, the purple is the side group, so it's the one thing that makes the different amino acids different is the side group. Then this is the nitrogen atom. The nitrogen atom is connected to a hydrogen atom that is hydrogen bonded to the C double bond O of the amide group that's immediately above it. And this hydrogen bonded network stabilizes the alpha helical structure. If you look at it from the top down, you will notice, and this is the free end here, that they just cut off kind of arbitrarily for the drawing because it's impossible to draw an infinite helix coming out of the board, so they had to end it somewhere. If you look at it and your finger is wrapping around in the way that the free end of the polymer, free end of the helix is your index finger, and it's pointing toward you in the direction of your thumb, then it's a right-handed helix. If it were oriented in the opposite way, it would be a left-handed helix. So the alpha helix is a right-handed helix. Interestingly, all the amino acids have the same stereochemistry, so all the bonds point in the same direction in amino acids. It's very interesting considering the origin of what's called biological homochirality. So why is it that all biomolecules have, or most of the biomolecules, there are some exceptions, have the same stereochemistry. So in the case of amino acids, you always have the same arrangement because there are two ways to orient the bonds in a tetrahedron, and it's always the same way. If you had one that was opposite in here, you'd get a bend here. You wouldn't have an alpha helix anymore. So why did that occur in the history of life? Some believe that it had something to do with a chiral catalyst, for example, in some mineral that formed the first biomolecules in preferentially a certain orientation. It could be because there was some cosmic radiation that was polarized in such a way to degrade enough of the molecules of the opposite chiral orientation to degrade them, and therefore only one of them was left over in the mix. It could be that chiral molecules were brought in from a meteorite that impacted the ground and sort of seeded the first homochiral biomolecules, but all that really does is punt to outer space, something that we could have explained on Earth, but in outer space it could be also a catalytic reason, or it could be cosmic radiation as well. Yeah.
Functionally speaking, if they had been seated the other way, do you think we'd have pretty much the same biology?
That's a really good question. The question is, if we had, if all of the amino acids had the opposite stereochemistry, would we pretty much be able to have the same life that we have now? That is an excellent question. My completely made up opinion is that we would have the same life that we have now, but all right-handed people would be left-handed. Just kidding. There is some evidence that in 1 part in 10 to the huge exponent, one chirality is more stable than the other because of the way that some particle physics reason. Now we can do a lot with the alpha helix. So the alpha helix can form hierarchically structured nanostructures. So this is the keratin alpha helix, and keratin is found in the hair and in fingernails and in structural proteins in animal physiology. So we have the alpha helix, the keratin alpha helix, and then two alpha helices bundled together to form a helix of helices, and then the chains are bound together to form a protofilament and then a protofibril. So you notice that we're well into the nanoscale regime now. We went from clearly molecular to now clearly nanoscopic, so 2 to 3 nanometers for a protofilament. The hair itself is quite nanostructurally complex, where if you start with the whole hair, which is on the order of microns in diameter, and then they are made up of the protofibrils and protofilaments, which themselves are made of these alpha helical structures. There's something called a perm, and after one has this done, not necessarily me, but once one has this done, what you do is these are the disulfide residues in the keratin filaments, and these are the side groups of the cysteine residues in the structure, and they form these disulfide bonds. And what you can do is you can reduce these chemically, which is why the perm process smells so delightful. And you reduce this chemically to form these thiol groups, and then you curl the hair up, and then you reoxidize it to form a new type of conformation. You can see that it's curved here with the new disulfide linkages, and necessarily because now we have less space on the inside track than on the outside track, you have some dangling bonds, thiol groups. And all of this, by the way, I stole from the Principles of Biochemistry by Nelson and Cox, 6th edition. And when you take 103, you'll buy the book, so it's okay that I took it now. Yeah.
So is the resulting, morphological change in the hair simply a result of putting it into one position and then letting the chemistry work itself out? So like they do perms where it straightens hair instead of curling it, would it just be the same procedure except instead of curling it, you hold it straight, the bonds reform, and it gets that new morphology? Yeah,
so the question is the new shape of the hair simply a function of reducing and reoxidizing the hair in a new macroscopic physical conformation, and is that how you can also straighten previously curly hair into straight hair? And that is indeed how it works. It's a little bit like a thermoset polymer, where, for example, 2-part epoxy that you might carry in your back pocket if you're doing home repair or something, and you heat it up. or just two-part epoxy tends to cure at room temperature in 5 minutes or less, or your money back, guaranteed. And what happens in those cases is that covalent bonds are formed in whatever conformation, and then it stays there. So these are actually cross-links, like in polymer science, where one chain cross-links to another polymer chain. We don't often think about it in this sense, but if you have a block of epoxy, or if you take two-part epoxy and you empty both cylinders all the way, and then you stir it up with a little wooden stirring bar, and it cross-links, what you pick up, and assuming it's completely reacted, what you pick up is a single molecule. Because you can go from one end of the polymer block to the other, even if it's a macroscopic puck of two-part epoxy, and you can find a percolated network of covalent bonds across the entire network. Highly cross-linked polymers are, in fact, single molecules, which is quite profound to me. Okay, so epoxy works by cross-linking. Yes?
So why can't you wash your hair after you get a perm?
I would assume it's because so the question is, why can't you wash your hair after a perm? And I repeat the question for the camera and also to buy myself more time to think of the reason. And I suspect that it's because physical, the mechanical action of scrubbing your hair causes bonds to slide past each other in the hair and undo some of the perm. I'm not sure what fraction of disulfide bonds it's breaking by washing your hair. But even after a few washings, it's going to be still pretty permed. By pretty, I mean rather, or quite, not pretty. Although I'm sure it is. Okay. Collagen is another type of structure found in biology, found in animals. And where do we see collagen quite often? Like JELLO. Where does gelatin come from?
Joints of bone and stuff.
So I thought it was primarily joints and bones and things, which it sort of is, but a minor component. Primarily it comes from, someone else said it, animal hooves, but someone else said something different. Pig skin. Yeah. So what you do, see, is you get the pig skin and you boil it, and then you separate the collagen out, which is hydrolyzed, and then you purify it and you get the gelatin. Forgive me for saying that. It happens to be true. So the collagen is the part of the skin, is the structural component that gives it its resilience. And now that we know from the stress-strain curve that resilience means more than just picking yourself up after you fall down, it's actually the energy density that's stored in the elastic regime of a deformable solid. And collagen is responsible for doing that. So collagen also has disulfide linkages between these helices. Now the collagen helix is different from the alpha helix. It's actually a left-handed helix. And the collagen triple helix is 3 collagen single helices helixed together, thusly. So here is the collagen helix. You'll see that it is actually a left-handed helix. So here's the molecular model showing the helical structure. Here's the space-filling model that kind of shows you where the van der Waals density extends to. And then here's the collagen triple helix, which itself, I believe, is a right-handed triple helix. And here it is from the top. And you can't tell anything about what's going on here. What's another structure? The beta sheet, which is found in proteins. So what do we know about a peptide bond? We don't have to know much about it, but we know that it enforces a planar configuration. So between the nitrogen atom, the carbon atom with the double bond to the oxygen, and the other carbon atom that has the side chain on it, those three vertices lie roughly, not totally, but roughly in a plane. And because of this planar conformation, as a consequence, they can tend to form long strands that can align with each other and lock together by hydrogen bonding, like this. So in this case, this is called the anti-parallel beta sheet. This could actually be a single polypeptide molecule with some coiled part over here, and then it comes back, folds on itself over here, and folds back on itself over here. And then in this case, the beta sheet is stabilized by the special type of Debye interaction, special type of Keesom interaction called a hydrogen bond. So this is the oxygen atom and then the hydrogen atom of the peptide nitrogen group. Now, could you also form an a beta sheet if the strands were all parallel? So they all went in the same direction, and that could occur if, for example, this chain went over here and then did some weird stuff and then came across this way. So instead of pointing this way, it was the same molecule but pointing this way, and that's what it looks like here. So these polypeptide chains could be derived from the same molecule, but then you have to do something over here that causes it to want to wrap around over here instead of just making the short turn over here. Or these could be polypeptide chains from different polypeptide molecules. Yeah.
The parallel or anti-parallel more stable?
The anti-parallel is more stable, and the reason for and that was actually my next point. So the anti-parallel arrangement is more stable because it's easier for the hydrogen bonds to get close together and lock into place. So notice in this case the hydrogen bonds are more or less in a straight line, perpendicular to the axis defined by the molecular axis, and in the parallel beta sheet form, there's some skew here. You can form even larger hierarchical structures of beta sheets called a beta barrel, for example. And this could be useful, for example, in biological channels where you're transporting ions or proteins through a membrane or through some other structure. So here is just a slide that summarizes the structure characteristics and examples of fibrous proteins. So these are proteins that give animal tissue its structural support. Now it says here the beta conformation forms soft, flexible filaments, so these beta sheet-like structures, and one example is silk. So the silk fibrin protein gives you is the main protein in silk from moths and spiders, and it's formed from the strong form of the anti-parallel beta sheet structure. And generally what's used by biology is the small side chains like alanine and glycine to allow the close packing of sheets, and the structure is stabilized by hydrogen bonding within the sheets and London dispersion interactions between sheets. So just like graphene sheets stack up to form graphite, beta sheets can stack up to form silk. So here is the silk space-filling model structure. You can see the anti-parallel arrangement. And then you can see here, in order to get these things to pack closely, remember I showed the slide with all of the amino acids. What you need is the small side chained amino acids in order to be able to pack this closely to have good van der Waals contact between the sheets. Okay, now what can you do with silk? Can we hijack the moth and spider silk apparatus? So can we take what amounts to a bunch of moth cocoons and boil them up? We like boiling up proteins in this class. You boil them up and you get you purify the silk, and can you make biointegratable electronics with them? So silk is very useful because you can make a stretchable substrate. We know it's stretchable. It has this, we know that it's biocompatible, and we know that ultimately it's biodegradable too. So you could take a thin silk sheet, a thin silk sheet. One time when I was an undergraduate, I was at a lecture from my dean at the time, and this was like first or second week of freshman year, and he got up and he said, "We will teach you to speak with precision." And I never forgot it. Anyway, so we can take these biological, these flexible sheets that are also stretchable and biodegradable and biocompatible, and we can put electronics on them that are also biodegradable and biocompatible and multifunctional, and we can put them on the body or we can implant them to make biomedical devices. So this is a very active area of nanoengineering that is largely driven by John A. Rogers at Northwestern, who's actually going to be giving the nanoengineering department seminar on Wednesday next week. So dissolvable films of silk fibrone for ultraconformal biointegrated electronics. So here's what you do. You take, comes from the boiled moth cocoons. So you boil up the moth cocoons and you cast the film, the silk film. This could be done by spin coating or by drop casting, depending on how. By drop casting, I just mean drop the solution and let the solvent, in this case water, evaporate, and you get a film. Or it could be spin coating if you need it thinner. And then this here is the flexible and stretchable transparent sheet. And then you fabricate your devices like your transistors and biosensors and capacitors and resistors and everything on a silicon wafer using normal photolithography that we talked about before. Then you transfer this structure to the silk film that you've made up here. Then you connect it using an ACF, which is an anisotropic conductive film, which is really just a piece of tape with a bunch of micron scale wires in it that you can address from the contact pads here. You can address them over here using laboratory electronics. So this is the schematic diagram here, and this is the photographs, or the micrographs as it were, of the structures here. It's less than a centimeter across, and what this is designed to do is to generate electrophysiological maps from mammal brains. So here it is. This is the brain. You prepare the electrodes in this. You open up the skull. I'm sure that's trivial. And then you prepare the electrode. Then you put it butter side down onto the brain surface. And because the brain surface, or the surface of the brain has asperities and wrinkles in it, you really require the silk, because the silk is stretchable, so it can conform to these nanoscale wrinkles without generating wrinkles elsewhere, or having areas where it's delaminated. So there's a difference between flexible and stretchable. So imagine a piece of paper which is flexible but not stretchable, and bonding it to a basketball. And you wrap it around the basketball, and it has to wrinkle in order to conform to the basketball. But if you have a sheet of really stretchy saran wrap or cling wrap, and you stretch it around, it will conform much easier without generating as many wrinkles. If it's really stretchable, it won't generate any wrinkles at all. If it's infinitely stretchable. So anyway, the point is that it's good that the silk is stretchable because it allows us to conform to the irregular topography of a mammal's brain. So, sorry, we've done some violence to animals in this lecture, but I didn't do it. This is a cat brain. And what the researchers did was they had a very thick backing film, and you can see that this has maintained its rigid structure. So this is 76 microns, and they put the thing on the brain, and you get a lot of poor signal here in the red. Then you reduce the thickness of the substrate down to 25 microns. These are polyimide films, so like Kapton, commercially known as Kapton. And then you have a little bit more flexibility here, and you get more green and signals better. But then you take the point of this exercise is to take the silk film, put it in, and then let it degrade by washing it with water. And what you're left over with is the mesh that is now conformed by capillary forces and van der Waals forces to the surface of the brain, and then you get a much better signal. What signal were they measuring? This is the visual cortex of the cat brain, and they were looking for evidence of signals lighting up on the cortex of the visual region of the brain, and showed that the signal is enhanced when the more conformal substrate is used. And the signal was the difference between the unstimulated state, so the cat is not shown an object, versus a stimulated state where you flash some object in front of the cat's eyes, and the visual cortex has some electrical activity that's detected capacitively by this device. But the point is here that you needed this silk structure in order to conform to the brain. So the Rogers group went on to coin this new term called epidermal electronics, where if you have a device that you want to attach unobtrusively to the skin in order to measure biomarkers in the sweat or light exposure of the skin, or electrical signals or electromyography in the skin, you want it to be as unobtrusive as possible. So what if there were a tattoo-like device that worked in the same way as a tattoo that you might get from a, I don't know where you get temporary tattoos these days, a Cracker Jack box perhaps, and you stick it to your skin, and you peel it off, and it's there for X number of days. So the idea is to make this a happy pirate character, but have it be instrumented with strain sensors, temperature sensors, electromyography sensors, so you can measure the electrical activity of muscles, and to do it in a way that's both unobtrusive visually, because who wouldn't want a pirate tattooed on themselves, and unobtrusive mechanically. So if you have the thing on your skin, you don't want to know that it's there, right? So you want to be able to ignore it. If it's really, really thin and it's stretchable, then you can ignore it much easier. How do we make metals stretchable? Well, one way to make metals stretchable is to create these zigzag and wavy and serpentine structures that have the effect of converting global tensile strains into local bending and unbending strains. Because it's much easier to bend something than it is to stretch it. Most things will bend if they're thin enough. Anything will bend if it's thin enough. Diamond will bend if it's thin enough. So what you do is you make it so that if you stretch this whole circuit out, then the tensile strain is converted to bending and unbending of these serpentine structures. So that's what the researchers did. And you notice that you have all kinds of stuff in here. This is the wireless power coil, so you can inductively power this device using this this wireless power coil, which is like a square spiral here. There are strain sensors in here, so they change their conductivity in response to mechanical deformation. There's a temperature sensor, ECG, so cardiography that you could put on your heart to measure the electrical signals in the heart muscle, and electromyography that you use to measure the signals in muscles. RF coil, this is for wireless communication. So you can, when an EM wave comes in and it resonates, say in the, this wouldn't be infrared, probably in the radio frequency, with the size of this antenna, then you inductively produce a current in here, and then you can also produce a current that can be read as an RF signal. And this is going to be a question that I won't know the answer to, but go ahead.
Are these things just engineered with built-in redundancy? Because I imagine with that many little tiny wires, it'd be easy for something to break.
In the lab, probably not. Probably what happens is instead of building in redundancy, you just throw out the 9 that don't work and you use the one that does work. But if you're going to manufacture it for a commercial process, yeah, you probably want to dot all your I's and cross your T's. All right, so you can detach these things from the skin later on, and they contain so little solid material, you can just chuck them in the trash or probably even let them go down the shower drain. And that is the power of nanoscale materials, right? So these are the circuits and the circuit components, and a little bit more of a detailed map. Here we can make transistors and capacitors and antenna and anything that we want. Photodetectors, LEDs. Now we can make an epidermal device using stiff components that have been rendered to be stretchable using these wavy device layouts. But can we also take the materials themselves, that is the active materials themselves, and make them physically transient so that the materials themselves can dissolve into a product that does not harm the human body or the environment. And combined with the silk technology, if you use the right metals and semiconductors, you can actually get stuff that dissolves entirely at biological pH. So this is a biological circuit made on silk that has magnesium interconnects, which eventually etches in the biological milieu. You have transistors that are made of silicon nanoribbons. If the silicon is thin enough, it will eventually dissolve at biological pH. And the magnesium oxide and magnesium transistors, so you use magnesium pretty much for everything because it will dissolve, unlike gold. So here's the construction of the device. Here's the device after 0 minutes upon immersion in a buffer solution, and then eventually the bulk of it starts to decompose, and then it's more or less decomposed here. So why would somebody, and here's the chemical details of how it works, but don't worry about the chemistry. So why would somebody want to do this? Well, there are many examples of a really horrible percentage of patients in hospitals get infected due to hospital-borne illnesses. Because what do you do if you put all the sick people in one building? People get sick. So, and one of the ways that we want to reduce this, or that the community wants to reduce it, is to reduce the number of times that you actually open up the skin to do a surgery. So if you have a device that is, and also if you have wires sticking into and out of the skin, then those are points of entry for microorganisms to give you a systemic infection that could kill you. So if you can wirelessly power a device and extract the data from it wirelessly, but also allow it to dissolve in the body, then you only need one surgery to implant it, and then you seal up the wound, and then after some specified amount of time, it will dissolve, and you don't need a second surgery to retrieve it. The person can go home. Ideally, they can even use their cell phone to transmit the data to their doctor. Yeah.
Did you say this is the kind of research that John A. Rogers is working on?
Yes. So this work is all the Rogers group.
Is there any work like this being done here at UCSD or in the area?
It's funny that you ask that. The answer is yes. We can talk more. This is okay. So this is the sort of menu of devices that can be made, not using our cell phones that we're texting on, but that is, please don't text in my class or whatever it is that people are doing. Okay. This is the menu of projects, of devices that can be made using dissolvable components. So diodes, resistors, inductors, capacitors, all with magnesium films and semiconductor nanoribbons. It's pretty badass, right? Magnesium, who'd have thought? And this shows you, this is another animal model. And this is a rat or a mouse that you'd implant the device in, suture it up, allow it to dissolve for 3 weeks. This is the tissue section. So you take the tissue and then you microtome it with one of these super sharp knives, and you image it, and you can see that over time the implant dissolves. And in fact, to get the time points here, you actually have to do this in multiple animals, and then I don't really have to finish that sentence. But anyway, so this shows you that ultimately the structure dissolves. Okay, that's all I wanted to say about the protein structure and the fibrous properties of fibrous sort of nanostructured proteins and what you can do with them. I want to say a few things about the use of proteins as biological catalysts, but any more questions about what I showed you before we move on? Okay, the other important function of proteins, and there are many important functions of proteins, are as biology's catalysts. So not just the structure, but also the machines that do the work. Like the ribosome at the beginning, although a ribosome has a significant component of RNA in it, which can still perform many of the catalytic functions of a ribosome even without the protein component, which is fascinating. So anyway, okay, so a protein, this is the space-filling model, has what's called an active site in it, and it binds one substrate or two substrates or three substrates, and it arranges them in such a way that they want to react. And what does that look like thermodynamically? So normally we're used to seeing this reaction diagram where we have a reactants and products, or we're calling it a substrate and a product, and we have this delta G dagger, which is the activation energy. So in order to get from substrate to product, even if the product is lower in energy, we need to overcome this barrier. And the transition state energy, which is where it's almost reacted but not quite reacted, is much higher than the substrate, so we have to overcome this. What an enzyme does is it lowers the energy of the enzyme substrate. It increases the rate by decreasing the delta G double dagger, and how it happens is that it has an active site that is complementary to the transition state between the substrate and the product. And what does this look like schematically? So once the substrate comes into the enzyme, it's the electrostatics of the system cause it to decrease in energy because it's bound to something, and because of van der Waals forces, unsatisfied bonds, van der Waals bonds like to be satisfied. But because we are in a state that is complementary to a transition state, the substrate wants to react to form the product. Then the product is still in the active site of the enzyme before it lets it go, and because of electrostatics, it's also lower in free energy. And then we go on to products. And this is the broken stick model. Forgive me if you've seen this already. But what if you have a stick, or you have an automatic slide advancer? Kinetically, entropically, this would want to be two pieces, right? So, but what's preventing it from being two pieces? Well, it's a whole thing, and it's connected by covalent and van der Waals bonds, and it doesn't want to be two things. So the not wanting to be two things is the large delta G double dagger of activation. That's like saying take the automatic slide advancer, or the stick, and ask it to bend spontaneously and then break into two pieces, just like that. Could it happen? Probably, but, well, not probably, but it might take millions of years. But anything with a finite probability of happening will happen, and integrated over infinity an infinite number of times, no matter how low the probability. Okay, so how do we get this process to speed up? Well, the bad strategy, the strategy that would not work, is to have the enzyme be the active site of the enzyme be complementary. In this case, we're saying that these are magnets, and say this is a metal stick. We don't want the active site to be complementary to the substrate, because then we would just fall into this energy minimum and never escape. What we would prefer is to have the substrate be, the active site be complementary to the transition state, in this case of the bent structure, and then break it in this way. So then the enzyme substrate complex, it comes in, it lowers the activation energy, it lowers the energy, a little bit of the enzyme substrate complex, but then what we have importantly here is that the transition state is now much lower in energy, so given some amount of thermal energy in the system, we can now break the stick into two sticks. And here's what it looks like. Thank you very much for your attention. I will see you on Wednesday next week.